We're on lecture number 9 of CIVE 360. Normally, since 9 divided by 3 is an integer, we would review today, but we just spent a little bit of time preparing for exam number 1, so we'll go ahead and forgo that. So we'll just say no review, again, only just because it happened to coincide with exam time. But you should go ahead and make sure you're kind of repping all of these basic principles, all these basic equations that we've been developing, so they really can come kind of quickly to mind. What we're going to do today is a couple of things. First off, we're going to go back to our expressions for axial displacement, and we're going to make it a little bit more complicated. So we'll call this axial displacement varying strain. Now remember, what we've done earlier was we've derived an expression for the axial displacement, and it looked like this. We have to integrate over the length of our bar the stress, that's P over A, and then we take the stress and divide it by the modulus of elasticity, and then we integrate the strain to get the axial displacement. But then we immediately made the simplification and said, well, let's go ahead and assume that P, A, and E are all constant. So it came out of the integrand, and we had our memorized formula PL over AE. And that's going to be very useful for us to be able to consider, because you've already applied it to statically indeterminate problems. There's a lot of problems where those values actually are constant. But what we want to do today is ask what's going to happen then when it is not constant. So our first objective in doing something like this is to figure out what is varying. So the first job is to determine what varies. In other words, is it the axial force? Is it the cross-sectional area? Or is it the modulus of elasticity? And frequently it's going to be really obvious. Obviously we've had some problems maybe where the Young modulus changed, and there we could segment it. So for example, if we have a bar where the area is the same, then all we have to do is we can apply this formula, but just do it in piecewise fashion. But what we're really interested in today is if something really does change as a function of position, and it's a continuous change, not just changing the modulus of elasticity over a couple of segments of the axially loaded bar. And so what we're going to do is introduce a type of problem where we do have that and see how to treat it. And almost always, in fact, I'll say the second job is going to be to set up and evaluate some sort of integral. And what we want to do in this segment of the class is really just get you familiar with it and give you a little bit of confidence that you can treat these sorts of problems without too much additional difficulty, because they're really not bad. At the absolute worst, you're going to have to either look up an integral in an integral table or use some sort of numerical technique. But it's to really get you to understand that there are some times when you are going to have to make that slight adjustment. So our teaching example is one that is going to bring that in. And it's going to be basically a cone that is fixed at the ceiling. So that would be what a top for T, tight, stalactite, something like that shape, or it looks like an inverted dunce cap. Most of you are probably way too young to know what that was. I happened to be watching a French TV show called The French Village, and they actually showed some kid who's wearing one of these things. But in any event, these are a shape that you're certainly going to be familiar with. So this is a axial loaded bar, and it's, again, fixed at the very top. And what we're interested in is the deflection as it's being loaded by gravity. So we'll call this a cone loaded by its own weight. This is actually a more complicated extension of something that is far more likely to occur, which would be something like a cylindrical bar that's loaded by its own weight, or a rectangular section that's loaded by its own weight. Those are actually going to be a lot simpler than this one. This one's a little bit tougher to set up, and that's why we're going to do it. So this one has a radius at the top of 2 inches. It has a length of 20 feet. Obviously, I'm drawing this not to scale. And it has the following properties. We're given that the modulus of elasticity is 10,600 KSI. And again, G is acting this way. So that's our symbol for the gravitational field. And then we're also given the specific weight. Now, unfortunately, in engineering language, specific weight is typically also given by the symbol gamma. So this is an ad hoc designation. This is probably going to be one of the very few times, in fact, maybe the only time that we use this symbol. But this is specific weight, and that is how much does it weigh per volume. So that's going to be equal to 0.1 pounds per cubic inch. And again, it is not shear strain. Unfortunately, we have to use them. If it were up to us, we probably would have used something like SW for specific weight. No, we probably would have stuck with gamma. Okay, and so this thing stretches then. It's going to move down some amount, delta, and that is what we would like to find. So let's ask the question then, what varies in this? So let's bullet that. And which one of our P over AE terms is going to vary? Well, here's one hint. What we're going to do is we're going to put our origin for our axial coordinate down at the base. So we're going to call that X. So our first hint is going to set X is equal to 0 at the bottom tip. That's useful because then you realize if you were to make a cut at X is equal to 0, you can pretty easily determine what the area is going to be and then also what the force is going to be. So we see that as we go up in increasing values of X, a couple things change. First off, the area, the cross-sectional area of that bar is going to get bigger. It's 0 at the bottom, and it's pi r squared at the top. So clearly, the area changes. We'll say A is a function of X. How about E? Well, in this case, E is a constant. So E is equal to a constant, so we don't have to worry about that one. And then what about P, the axial force? Well, the axial force is actually being caused by the chunk of the bar where we're making our cut. So if we go back up here, and I cut off a piece of the bar right at that location, that's a pretty small tip. It's not going to weigh very much. If I go up here, it's going to weigh more. So clearly that is going to also vary as a function of X. So we write it like that. So we've got two things that vary then as a function of axial position, and it's our job then to determine what those are going to be. Well, let's go ahead then and take some arbitrary height. Let's just go to X right there, and we're going to cut it at that location. Now remember, you probably learned this in your statics class, that as soon as you define some location, you can really treat X as a fixed distance. So now we've got the cone, and now rather than being an arbitrary axial coordinate, we get to keep that as being some fixed distance. So when you do this, you get to treat X as, at least for this shape, it's going to be fixed. So in other words, you can identify whatever that value of X is going to be. It could be 1 inch, 10 inches, and so on. And you can treat it as a fixed distance. A lot of times, when you're first learning this, you're a little bit timid to go ahead and do that. But as soon as you make that axial designation, then you can say, okay, X is my actual length that we've got. So our job then is going to be to figure out, first off, what is the area at that location, and then also what is the axial force at that location. Well, everything is going to key then on that area. So we're going to now draw a side view of this cone. So here's what it looks like from the side, like so. And then I'm going to draw the dashed line right there. Now we can see once again, just like we had compatibility for the rigid link problem, we notice then that the radius that we have at our value of x is a case of using similar triangles, because we see then that the radius up here, which is 2 inches, that is to the axial distance, which was 20 feet, so that's 240 inches. So we can say the similar triangle set up to find the radius is that 2 is to 240 as r, where we want it, is to x. So we could write that as r of x if we wanted to. So 2 is to 240 as r of x is to x. So we see then that r, the radius, is simply going to be equal to x divided by 120. So that is a crucial, I'll put a dash box around it, because getting the radius then really is going to influence all the parameters that we need to set this problem up. So now we can find a of x. So the area that varies as a function of x is going to be the pi r squared, I should say r of x squared. So we've got pi times the x over 120, the quantity squared. So that is our a of x. There we go. So now we have a of x, and we also know that e is going to be a constant. So e is equal to a constant. So the only thing that's left then is the axial force. And we'll pick up that as we start part B of our lecture, but part A is wrapped up.